guys, today we're going to go over 5.2 probability. We're going to go over most of it. We're going to leave the Venn diagrams for another video tomorrow. So in order to begin a probability model, let's go over to the first definition, probability model and sample space. A probability model is a description of some chance process that consists of two parts. A list of all possible outcomes, like tossing a six-sided die. These are the possible outcomes. And also a second part, the probability of each outcome. Each one has the same probability in this case. Sometimes you won't have the same probability. In this case, they do. So 1 over 6 each one. Just do the divide, use decimals. It's better to work with decimals, so it doesn't look like a ratio. And the list of all possible outcomes is called the sample space. So again, this would be a probability model, the outcomes and their probabilities, probability model. The outcomes would be the sample space. Okay, now let's go over an event. The definition of the book says an event is a collection of outcomes for some chance process. Let's use the same example of tossing a die, and the example in the book is pretty good. Let's say if I roll two six-sided dice, what are the chances that I end up with a sum of 5? When I add two numbers, what are the chances, I end up with 5? So the event would be adding up to 5. And now we're going to go over the collection of all these outcomes that can give me that sum of 5. You can have the first die rolling a 1 and the second die rolling a 4. That gives me 5. I can have a 2 and a 3. I can have a 3 and a 2. So even though this is 2, 3 and 3, 2, even though they're the same numbers, we have different die rolling different outcomes. So you do have to count them. And the first die can roll 1, and the first die can roll 4, and the second die can roll 1. So the event of rolling a 5 could be summarized with the following formula that's provided. Number of outcomes that add up to 5 divided by total outcomes. So favorable outcomes adding up to 5 divided by total outcomes, all possibilities, including the ones that add up to 5. So this is all possibilities. These are the ones that you're looking for. So in this case, I would end up with 4 possible favorable outcomes divided by a total of 36 possible outcomes. Each die can roll 6 sides. I have 2 dice. 6 times 6 is 36. So again, the event of rolling 2 die and the sum is 5 would be this, and when you divide, that gives you 0.11. Okay, so again, favorable outcomes divided by total outcomes. Now, right now, we're focusing on a single event. Later on, we'll see that we have mutually exclusive events and a couple of other ones, and that's when it gets a little interesting. Now, note, this subject has some relation to set theory, and we're going to be using Venn diagrams, unions, intersections, and other words like complement. When we went over set theory, the complement was what was this missing to become the universe? The universe being everything. Since everything in probability would be the number 1, meaning 100%, the complement of this event would be 1 minus the probability of that event happening. The probability of this event happening is 0.11. So the complement would be 1, which is 100% of the universe, minus this. That's what's missing. And it would be 8.9, yo estoy lentísimo, 8.99, I don't know, figure it out. Or 0.899, let's see, 10, I add 1, I think that's it. I'm a little slow, it's a little late. But pretty much the complement is 1 minus the probability of your event happening. And it's the same thing as saying like not 5. What are the chances of not rolling a 5? It would be, not rolling this probability chance. So it would be the remainder that add up to 1. So there are different ways to see the complement. If they ask you for the complement, you know it's what's missing to become 1. If they tell you the chances of not rolling something, they're usually referring to the complement. The chances of an event not happening. That's the complement. Okay? Now we're gonna go over mutually exclusive, or the concept of mutually exclusive. Now in real life, you can see mutual exclusivity in many ways. We're gonna talk about them later. But the book right now focuses on using dice, and I really like that because it's pretty clear cut and simple to understand. Now the example in the book, which is pretty good, it says, what are the chances that the sum of the dice is going to be 5, which is here, or 6? Now let's do an exercise. Let's see in what ways I could end up with a 6. The first one could be 1, and the second one could be 5. The first one could be 4, the second one could be 2, 3 and 3, 2 and 4, 5 and 1. So the probability of rolling a 5, or that the sum of the two dice is either 5 or 6, would actually be the sum of this probability and the sum of this probability. So when you're working with mutually exclusive events, you have to use and. It's and. This and this. And in statistics also, it's more or less like an addition. You'll see it changes somewhat. But why are they mutually exclusive? You can see that none of the results that are in this event are repeated in this event. I do not have a 1-5 anywhere here. I do not have a 4-2 anywhere here. I don't have a 3-3 anywhere here. And vice versa. None of these results are here. When this happens, it's mutually exclusive. They can happen independently. One can happen or the other one happen, but the results aren't repeat. That's the important part. Whenever you don't have any repeat results, you're talking about a mutually exclusive event. Either this happens, or this happens, or they don't happen. You can't have both happen at the same time because that wouldn't make them exclusive. So again, the word tells you, mutual exclusivity, mutually exclusive. It's either one or the other, or they don't happen. So whenever this happens, it's a straight up addition. You add the chances of this happening and the chances of this happening, and that's the result of rolling this or this. And I'm sorry, I said and, I meant or. Rolling a 5 or a 6. My bad, I'm the math teacher. So again, or. Rolling this or this. Mutually exclusive. This can't happen. None of what happens here happens here. Okay? Now, let's go over the next example, which is very interesting. And they use a table to describe non-mutually exclusive events. And here's where you're gonna get a better idea of what's happening. So here I have pierced ear, yes, no. And here I have male, female, assuming they're two genders. Nowadays, let's just assume two genders. Don't cancel me, please. This is what's in the book. So I have 1984, 71, 4. And then, this is a two-way table. I have my marginal values. So I'm going to have a 90 here. When I add this, I'm going to have an 88. I'm just going to use the book. It's going to be easier. 103. 75 and 178. Now for this example, let's go over A, B, and C. Now whenever they're asking me probability of B happening, B refers to pierced ear. And probability of A happening, A means male student, regardless of whether their ear is pierced or not. So let's go over the first example. It says probability of B happening. B is pretty much a pierced ear. So I look at my yes table, I have 103 students with pierced ears. And those are my favorable outcomes, and I divide that by my total outcomes, 178. Divide that, that would be the probability of having a student with a pierced ear. Pretty straightforward. Nothing crazy there. Now, let's go over the second one. Find A and B. That means that you have to qualify for both A and B. It has to have both A and B. A being male and B being a pierced ear. So the probability of finding a male with a pierced ear is 19, those are my favorable outcomes, over 178. You divide that, and that's going to give you the probability. Now let's go over the third one. Let's find A or B. Let's find A or B. Now, for A, I have male patients. I have 19 plus 71. I have 98. And for pierced, I have 103. But the problem is, I already counted my males when I added my A probability. I cannot double them and add them again when I go over my pierced. So one way to work with tables is if they ask you for multiple things. For example, I have to find, let me erase this circle, I have to find my male patients, and I have to find my pierced patients. If you have more than one oval circling a particular value, that means it's already counted and you do not count it again. So I would count this once, I would count this, and I would count this. Remember, these are total values, so you don't add the totals. If you want to work with totals, you can just add the totals, but subtract the double counted values. So you can either add 19, 71, and 84, that's one way, or you could add 90 and 103, but you have to subtract 19. Add those elements, divide by 178, and that's the probability of finding a male or a pierced ear person. Remember, when you're counting probabilities, you can't double count your answers or you're going to have crazy results. Sometimes you might get probabilities over 1, and that should be an immediate red flag when probabilities go from 0 to 1. So don't double count your subjects, okay? You either subtract them from the totals or you add all the cells one at a time without double counting. Está bien. And one way to do this, and again, and this was not a mutually exclusive event, because you could have a male and you could have a pierced ear, and in this case, the outcome would be repeated, both in pierced ears and males. This outcome is repeated, so this would not be a mutually exclusive event. Having a pierced ear does not exclude you from being a male subject and vice versa. Being male doesn't exclude you from having a pierced ear. Since they share common outcomes or events, they will not be considered mutually exclusive. The formula to calculate this also, the formal formula is given in the book. And it says the probability of A or B happening, all you have to do is the probability of A plus the probability of B minus the probability of A and B happening. A and B happening would be the repeat numbers, where both this happens and this happens. So you add this, and then you subtract the probability of when they both happen. It's pretty much what we went over in the previous example. That's it for today. We're going to have another video tomorrow for Venn diagrams, but this is the more important part of today's class. recognizing when events are mutually exclusive and non-mutually exclusive, and when you can just add everything together or add everything and subtract repeat outcomes. Have a great day. I'll see you tomorrow.